All right, we'll go ahead and get started. So if you haven't already, make sure to go to dsuprog.club, join the meeting. That way we can take attendance, and then you can follow along in the slides. So tonight we'll recap the ICPC regional competition that took place not last weekend, but the weekend before. I think time flies by. I haven't kept track of it lately, so sometime. So yeah. So a little bit about the competition. For those of you who competed in the ICPC qualifier that was taking place here at DSU, it was similar format, but there were a few differences. First difference is location, obviously. So we all traveled out to Minneapolis, and we competed on the University of Minnesota campus in one of their buildings there. So we send 3 teams of 3. So those 3 teams of 3 were decided from the qualifier there. One fundamental difference about the competition at the regionals was that there was only one computer allowed. So at the qualifier, everyone was able to have their own computer, write up their own code, test it on their own computer. There was only one computer that could submit to Caddis, but you were able to code everything on different computers and stuff. We only had one computer at our use. So the other 2 were pseudocoding on paper, essentially, and then would shift that paper over to the person running the computer, and they'd type it up, or you take turns sharing the keyboard, whatever your strategy was. I know that my team of me, Nick, Aaron, we followed. Aaron was primarily the typer, and then Nick and I were writing up solutions on paper, and then giving them to Aaron to type out and submit. So once again, the answers were submitted on Caddis like they were for the qualifier. And I put closed internet in quotations, so you had access to the basic documentation pages, so like C++, C++ reference, or like the Python docs, but it wasn't like wide open Google. Like you couldn't, like, there was some algorithm that you knew that you needed to use, but you didn't write it down prior. You weren't able to go Google that sort of thing. But it was like open notes, open book sort of thing. So if you had like a textbook that you had in one of your classes that you wanted to bring along, or we did is we made a 20-ish page document full of important functions or algorithms that we could use that were all in Python. Funny story with that is that our team decided to use Python literally, less than 12 hours before the competition instead of C++, just because it's...
It was longer than 12 hours.
Okay, it was longer than 12 hours, but it was a slightly last-minute decision. But reasoning for that was, it's just quicker and easier to use Python for like these competitions, and the compiler that Caddis uses for Python translates it so it runs as fast as C, because that's one thing about Python is that traditionally it runs slower than C in terms of execution, but the compiler that Caddis uses made it as fast, so there was no drop off in runtime, and then from there it's quicker and easier to code things up rather than like I think Aaron was talking about he wanted to like do like some mapping thing in C++ and how it was going to be kind of gross, and then we realized, oh, in Python this is a lot quicker and easier. So that was kind of the motivation behind it. A lot of the syntax is pretty similar, but anyway, here's our all of our functions. So we printed this thing off, killed a tree in the process, but that's okay. And so here are all the different functions. We did not use all of these, obviously, but there are certain ones where like, oh, hey, this function will be helpful. And then we found it in our pages, and it was good and ready to go, with the exception of one function was copied and pasted incorrectly, so that was kind of a oof. But otherwise, it was helpful. So that's kind of the parameters of how the regionals was set up. So advice to all you future competitors in the regional round is, make sure you kind of have like those notes and stuff ready at your disposal. Obviously not required, but obviously it helps out a lot in those moments that you don't have to try and remember how that function goes, or if it was like a sorting algorithm or that you learned in algorithms and optimization, for example, like having that printed off ready to go. That way you don't have to try and remember, okay, how did merge sort or quick sort work, sort of thing. It's just one example. So yeah, that was kind of like I said, the ground rules of the competition here. So we did have 3 teams as mentioned, and so out of 96 teams that competed, we had 3 teams that finished in 14th. That consisted of Blake, Julia, and Ben. 26 was me, Nick, and Aaron, and then 50th was Galen, Jake, and Shane. So out of our 9 competitors, we all went. So good job to all of y'all, and thank you to Austin O'Brien and Mark Spanier for being our transportation in the vans and stuff. So round of applause for that. We had a really fun, intense 20-question session on the way back from the competition in Austin's car. So that was pretty fun. So if you want the official scoreboard to see how everyone else did, it's linked in here. The team from University of Wisconsin-Madison got all of them solved with like an hour left to go. It was insane. So I don't know. I guess at that point you just go home with an hour left on the clock. I don't know, but so that was pretty insane. And there you go. There's our first DSU team, etc. So there's a link for that if you're interested. So same as the qualifier recap, we'll go through a couple of the problems that were presented to us over the competition. You can get the link to it will be attached in here, so you can go and check out all the problems if you wish. And then we also have a solutions file somewhere, PDF.
Is that the one with the problem tax?
The what?
Is that the one with the problem tax?
The solution one or the
Caddis thing?
It does have the problems. Like if you click on problems up here, and that has all of them. So, and then the ones that we're going through, I have hyperlinked right into the slides as well. But so if you just go to problems, you'll have the list of all of them there. So, and then I think there is a solutions PDF out there somewhere that's kind of just like in text. It doesn't have actual code solutions, but it kind of walks you through of the strategy of what to approach. So we can try and get that up to the resources page. We don't have that up there right now, I don't think, but we can easily add that. So the first one we'll go through is problem G, code guessing. So this is the one that I got to work on. So a little background is that so Alice and Bob are playing a board game. They have a deck of 9 cards. So Alice gets 2 cards, Bob gets 2 cards. They're numbered from 1 to 9, and there's only 1 card with a digit on it. So essentially what happens is that Alice gives her cards to Bob. Bob sees the digits on Alice's cards and then lays all the 4 cards down the table in increasing order. So basically what happens is we know which 2 cards are Alice's. We need to figure out what Bob's cards are, and we need to determine if we can figure out what Bob's cards are and make sure that is laid out in increasing layout sort of thing. So if we can accurately predict what Bob's cards are going to be, we output them. If we cannot predict what Bob's cards are going to be, we output a -1. So for example here, 6 and 9 are Alice's cards, and it gives the orientation as well of what orientation is to make sure that the cards are in increasing order. So as you can see for this one, Alice has the lowest card and the highest card. And because she has 6 and 9, and we know that Bob's cards are in between, we know that it's 7 and 8, so 6, 7, 8, 9. But for 2 and 5 are Bob's cards here, and Alice's are inside somewhere. Wait, take that back. 2 and 5 are Alice's cards, and Bob's cards are on the outside somewhere. So we can figure out that Bob's card on the left is 1, because there can only be 1 digit less than 2. But on the other side of 5, it can be 6, 7, 8, or 9. And we don't know which one of those it can be. So because we can't definitively say what Bob's cards are, we output a -1. So pretty straightforward in terms of the problem and what the goal is. So the first thing that I just kind of started doing, I'm like, well, let's just lay out all the possible scenarios of the card orientation and see where we can go from there. So that's why I started here, and I quickly learned that with the exception of ABBA, where Bob's cards are on the inside, that one requires a little bit of math. All the others, there's only like one possible scenario with that orientation I quickly learned. So for the first one, Alice's cards are the first two and Bob's are the second two. Just remember that all the way throughout we want to solve for B, basically. So I first read in these two, Alice's two cards here. So I did AL for Alice's left card, AR for Alice's right card. This is basically saying that it's reading in the input, we're splitting on white space, and we're converting that to an integer. So basically this is 2% D's happening in a Python way. And then below that we have S, which is reading in that orientation string. So we just have that labeled as input. So if the string is, we'll come back to this first one. If the string is AABB, meaning Alice's two cards and then Bob's two cards, all we need to check for is that Alice's right card is 7, because then we know that the only two cards that can be greater than 7 are 8 and 9, and we can print that out. So it doesn't matter if it goes 1, 7, 8, 9, 2, 7, 8, 9. They just need to be in ascending order is all, and we just need to be able to predict Bob's cards. So yeah, with Alice being right 7, we know that those last two can only be 8 and 9, therefore we can print it out. Otherwise, if it's like 1, 2, and then 5, 6 sort of thing, we don't know. If it's 1, 2, and the right number is 2, we don't know what those other two numbers can be. It could be 3, 5, 4, 8 sort of thing. So therefore, we print -1. The second argument is ABAB. So if the left card is 6 and the right card is 8, then we know it can be 7 and 9. That's the only scenario that works. If it was like 5 and 7, that rightmost B can be an 8 or a 9. And since we can't definitively decide, we print out -1. So kind of follows the same format here. Python syntax says elif is just an else if. So this BAB, we know that if Alice's left card is 2 and right card is 8, then it can only be 1 and 9. Any other values, you can't determine what Bob's cards are. If AL equals 3, then it can be 1, 2. If AL is 2 and 4, print 1, 3. So BABA there. And then that last one does require a little bit of math, but so it's just checking that if Alice's cards are on the outside and the difference between them is 3, then we can determine that those two middle ones. So if it was 1 and 4, 4 minus 1 is 3, then we know that B and B can be 2 and 3. So we can run a sample here. So 6 and 9 was the example here, and then ABBA. Nice is right. See output 7 and 8, 2 and 5, BAB. -1. And I can do other examples, but I don't want to try and do math in my head really fast to make myself look like an idiot for getting the wrong expectation. But you kind of get the picture there. So as I said, it was pretty straightforward. Going into it, I didn't know if there were going to be more scenarios like this math one here, where you have to do a little bit more math. But nonetheless, I decided just list out all the possible string variations. And then as you go along, you kind of realize that, yeah, there's only one possibility for all these except one, which made it nice and easy to solve. So yeah, pretty straightforward. Any questions with that? Sounds good. So the next one that we worked on as a team was problem C, which was subprimes. So for that one, that was kind of Aaron's main one that he worked on. So I'll give the stage to him for that. So.
So this problem, let me control click it. Basically, all it was is you were given an input, say that first line 1 to 10 is saying from the first prime number to the 10th prime number. And all of those, we need to find how many of them have a substring of that second number. So in that first one, and all the prime numbers between the first one and the 10th one, how many of them have a 9 in them, and then we print that count as our answer. So the big fun part with this problem is that there are up to 10 to the 5, that many, that's the biggest prime number, but like place-wise, so the actual number is significantly larger than that. Conveniently though, mathematicians are very smart and they've developed algorithms to find all of the prime numbers. I don't know it off the top of my head, but in our handy-dandy algorithms PDF we had one. It's a sieve is what they are called. So this this function right here, this sieve of fancy Greek mathematician guy, I didn't write this. I just wrote it from the our PDF. But fun story about this problem, we didn't actually solve it during the competition. I solved it the day after. Because when we were doing our initial testing of writing this, the sieve and then finding all of the prime numbers, we thought we were going to get a time overflow. So we decided, instead of just trying it and hoping we didn't get a time overflow, we skipped straight to trying to optimize it. And since optimizing is very hard, we ran into some logic errors. I think we hit an off by 1 error in like several different places in the code. So if we subtracted a 1 here, we'd hit off by 1 error somewhere else, and it got really messy really fast. And then afterwards, we realized you could just do it. So all this problem does is it gets our first input, the low and the high, and then the input of our substring. It finds every single prime number from the first prime number to the 10 to the 5th prime number. And then I loop through the subarray of the numbers that they gave us, and then I just check if the substring is in that number, and then if it is, I increment a count, print the count, problem solved. So it's kind of a thing of, even if you think you might hit a time overflow or a memory overflow or something like that, it might be worth to try it and just see if it works. So that'd be that problem. Next, I think it's you, Nick. I got you.
Hello. This problem is called stream lag. And basically, all you gamers out there will be familiar with this problem. Because basically, it's the concept of you've got a live stream that's sending, in this case, a packet of a single second worth of video at a time, but they might not necessarily all come in order, and they might not all come in time to be played in real time. And that's where lag comes in. And so basically, you're given a list of all the packets and at what point in time they arrive to your PC, and you have to figure out how many seconds of lag there will be if it tries to play them in order starting from second 1. So basically, so the input is, the first line is the amount of packets that there are. All the following lines are times followed by what packet was received at that time, and there can be multiple packets per time, but that's, as you can see here, the duplicates are listed separately, so that makes input fairly easy. So for this, just read in n, and then I made an array, and for all of the rest of the input, I created what's called a tuple out of the time and the the packet number, and just threw that into an array. And then I turned it into a dictionary, which is basically where you've got a key and a value for that key, where you say, okay, I want the value that's at the key of like 5 or the letter Q or something like that. And then it will say, okay, that's the value that you put there. So I'm turning it into a dictionary where the key is the number that it is, and the time is the value. So you can give it what packet you want, and it'll say it was at this time. You can, in this case, you could have also pretty easily done it with just an array. But I was using Python, so dictionaries are fun. And then once you've got that, you can essentially just simulate the experience of watching the video by keeping track of C, which is the current, or what the next frame of video will be, and X, which is how far along you are in seconds. These are both initialized to 1 because the problem does that also. But basically, until you've read through all of the packets, you check to see if the time that the current packet was sent was less than or equal to the current time, which means if you're at a certain amount of time and your current packet is available. In that case, you increment both what your next packet is and what the current time is, just by 1. But if it's not there yet, then you gotta figure out the difference in time, which is how long you gotta wait. You add that to your total lag time, and then also to your seconds. Then it'll just jump forward to the next packet, and then you're done. That's all it has to do.
Boom. All right. Thank you, Nick and Aaron. Any questions from any of you or Team Dunder Mifflin Scranton? Any solutions that you want to share that we did not cover? And if not, that is perfectly fine. We also have a new problem set that should be posted right now, so that'll kick in on standard time, so like right after meetings here. That'll run through next Wednesday, so if you're bored over the first half of your spring break and want to do some problems, go right ahead and do so. So that's open there. And then we will get those solutions posted. So like I said, it's just kind of a text description, kind of like what we did today, just kind of talking through it, not actual code file solutions, but yeah, you get the picture there. So next week, obviously spring break, so we will not be meeting here, obviously, but 2 weeks time, we'll be back here. I think we'll have Nick talk about Godot. So those of you interested in GUI stuff, 3D specifically, come check that out in 2 weeks' time. Other than that, we will call that a meeting for tonight. Thank you for coming, and have an awesome spring break. Stay safe, don't die, and we'll see you soon.